where we were paying, over $1,000 a megawatt hour for just this past summer, 2.5 months ago. And as your load continues to increase, the issue becomes we can't supply that load. And so what they do is they start putting out contracts for futures contracts. We're going to start paying more money per megawatt hour, per kilowatt hour. And so then you, as an investor, makes the decision, we can make 10% rate of return, 15% rate of return. We want to grow our business, right? Because that's how the stocks continue, right? You sell more widgets or you sell more kilowatt hours. And you're incentivized because you're like, yeah, I can get 5 cents a kilowatt hour or 6 cents a kilowatt hour in 5 years. So I better build my power plant sooner than later because I'm incentivized to do that. So it really is, the load has to be projected to be there. Doesn't necessarily have to be there, has to be projected to be there, because some of these plants take 3-5 years to build. And that's from the day that somebody says, okay, let's go ahead and build a plant. You got to get permitting. You got to make sure the utility doesn't have any issues. You have to study the system. It's a really long process. And then once you're ready to build a plant, less than a year to build it, but it might take 3-4 years. So they're projecting, hey, this needs to be done. So this is all based on what these utilities and the ISOs will predict the future load will be. And that's a really hard thing to do because maybe 2 years ago, EVs were going to replace cars, right? I mean, Volvo switched to all EV technology. Maybe they stopped the process, but I think Audi or Volkswagen was looking. Mercedes said this is their last combustion engine that they're going to design because it just looked like EVs were going to eat everybody else. And then all of a sudden, administrative changes for one reason or another made it so that it's not necessarily going to be the case, at least in the near term. So that makes it difficult to anticipate what's going to happen. So yeah, you got to predict these things because you can't, like I said, go to Home Depot and pick up a 50 megawatt generator and plug it in. It just doesn't exist that way. So you need time. And there are people that just actually do it. So I like to put this up. So prices slightly higher than they were on Tuesday. And look at the demand. It was about 10,200 megawatts, if I remember correctly. Now we're at 10,600 megawatts. Pretty good. The forecast and the demand is almost exactly the same. But the costs are a little bit higher. Not a lot, but a little bit higher. Still in the green, right? Still a good thing to do. And you don't even have to go to New England if you want. You can go to New York ISO. And they have the same information. So right now, theirs is about the same as ours, $26.85 per megawatt. And then you can see the demand is, where's the demand here? That's PGM. They always change these things. It doesn't make it so easy. This is actually, we got to go real time, not day ahead. Actually, so they're paying $37 a megawatt hour. So they're a little bit higher than us. And their demand right now is 17,690. So about 7,000 megawatts more. So their prices are a little bit higher. One of the ones I really like to check out for crazy price swings is California. So if you go to California ISO and you look at their current demand is 37,000 megawatts. Just a little bit bigger than what you find here, right? And then if you look at, where's our market information? Normal, usually they have more information that's readily available. What's that?
Market operate.
We'll try that. Today's Outlook network. I don't know if that's what we want. I'm having a hard time finding it because normally they have more information here. We don't want the calendar. We don't want that. Let's see what today's Outlook looks like. Okay, so there's some information about the megawatts, and you can see, again, as it gets dark out, right, the demand starts to peak. But it would be nice to know what the costs would be. Let's see.
Twice,
Go ahead. What's that?
twice.
Yeah, demand supply emission factors are the,
Oh, thank you. So you can tell 9:25 Pacific time, and it's kind of broad. So we'll just kind of zoom in a little bit, and you can see that they are pretty low. Not as detailed, but $41 a megawatt hour. You know, again, depending on where you're looking. Let's see the blues here. Minus $1.59. What's the problem having negative costs for electricity? That means they don't want it. There's too much power on the grid, so they're going to pay people to take it away. And so what that is there's a massive amount of solar there. So these people are actually saying you got to actually draw a load. So we're not going to pay anything. We actually have to get people to take it in. So there can be some negative costs. In that case, just dump it. You know, don't even generate, just dump the power. So if you want to like take a look at California, that's the biggest one that there is that I know of, but they have a lot of different stuff. And I do have some slides in a different class for a little while ago, but they were over $1,300 a megawatt hour. So some real problems when you do that. Okay, let's take a look at some data for loading. And I got this data right off of the ISO New England website, so you can access it too. I just put it so that it was in the chart. But here shows some of the variability, whoops, of over the course of June. And I picked June because that was the same month that we had that peak, you know, that 24th. I don't know why the screen is acting so weird. But you can see on the 24th is when we hit almost 2,100 megawatts of demand in the state of Maine. So again, the state of Maine is just a small microcosm, but you can see demand sometimes is 800 megawatts. And in less than a month later, let's say 20 days later, now you're pulling almost 3 times the minimum demand. So your system has to be able to ride up and down and still try to maintain low cost, but hopefully ensure very high reliability, all while doing that kind of variability. So it makes it very difficult. That's Maine monthly. How about a week? Again, that's that one inclusive week. And over the course of a week, you were just under 900 megawatts, all the way up to almost 2,100 megawatts. Again, that system has to respond. This is 4 or 5 days difference, and it's got to be able to handle that. How about a course of a day? So this is that bad day with really high prices. So that day, because it was so hot, we weren't at the 800 or so megawatts. We were down to 1,200. So quite a bit of a difference. But again, we had to peak up. So in about 12 hours, we went from 1,200 megawatts to like 2,050 megawatts. So what is that? An 80% increase in the demand for our system. So pretty big change. And if you think about, you know, any real world stuff, how hard it is when you have such variability, and the system has to be as efficient as it can be. So it can handle this. It just poses some real challenges from an electrical perspective. And then I just included New England, and I included this a little bit just so you can see how closely we track to the rest of New England. So this does a pretty good job of indicating how we compare. You see Maine is the blue line and orange is New England. So we're not exact. You can see that our peaks aren't as high and our drops aren't as low. So what this tells me a little bit is that Maine, for some reason, may be more efficient or more energy aware and more conservative, right? If it's going to be a super hot day, I'm going to have my air conditioning on, but maybe I'm going to turn it up so that it's 78 in my house as opposed to 72. so I can use a little less. Or it could be weather dependent too, right? Maybe it doesn't get as hot in Maine, so you don't need to run your air conditioners quite as high. But you can just check and see how it tracks with those. And I've got two axes here. Hopefully you understand that. The left axis is for Maine because it goes up to about 2,500 megawatts. The right axis is for New England. So you can see that it's 27,000 or so megawatts for the orange line, because obviously the scales would be quite a bit different if we just tried to compare them. So we have a power system. What are we going to do? It's really make sure we get paid. And how do we get paid? Deliver a quality product. A quality product is feeding load within a range of voltage, a range of frequency, and frequency is actually very tightly controlled. Voltage is a lot more variable, but frequency is very tightly controlled. And the reason why voltage is got to be controlled is I don't want to plug in my laptop here and the voltage on my plug-in be at 800 volts, right? Which seems absurd. But if you allow a lot of variability in your voltages, you could actually damage equipment. And there are rules about plus or minus 5% is what the utility is allowed. Once you start going outside those bounds, you have to take corrective action. If you don't, the utilities could be responsible for damaging your equipment. Minimum cost, you'll notice it says usually, but it's not. They try, but it is what it is. You're going to have to pay because the number one thing is high reliability. So reliability is way more important than minimum cost, because if I didn't care and I was allowing to have very low cost, then if my reliability was questionable because I didn't have a lot of spinning reserve or I didn't have a really well-maintained system, then yeah, I can go much, much cheaper. But here, we want high reliability. It is so essential to our lives that is actually a higher value. The project management run, the three overlapping, the Venn diagram, we have cost, schedule, and quality, right? Pick two out of the three. Over here, you really just get to pick one. It's high reliability, and you just deal with the costs. Still okay cost, but we have to do reliability. What are we going to cover? We're going to model our system, because as engineers, we don't have to go out in the field and get our hands dirty. We like to be able to analyze systems as best as we can without having to actually, run tests on them. So we're going to convert transformers, motors, generators, transmission lines, all those things. We're going to convert those to resistors, inductors, capacitors, and power supplies. Because we know KVL, we know KCL, we can do analysis on those if we know what they look like. So we're going to take those transmission lines running from Orrington down to Windsor, Maine, and we're going to convert that to a bunch of resistors, inductors, and capacitors. We're going to do load flow or power flow analysis, and we'll even discuss some of the control aspects, and you see how you can almost know exactly power flow based on magnitudes and angles of voltages. We will try to discuss economic system operation, but understanding the LMP, the local marginal price, means you got to do a lot of partial derivatives. See it there? That's the LMP is essentially the result of doing what ISO New England provided for prices, is looking at some partial derivatives and coming up with the least cost. We're definitely going to do short circuit analysis, because none of the system will fly if we can't protect it for short circuit. So the system doesn't even exist unless we can ensure that we can remove all faults. And then we'll talk about some of the ways to isolate those faults, because we know they're going to occur, but we will isolate them and limit the amount of equipment that's taken out of service. Clearly, if we have a fault, we could take out all of campus. So if I plug in my laptop and I have a short circuit here, I could shut down all of campus. That's probably not a very good thing. Why do you think that's not a very good thing? There's a really obvious reason and a not so obvious reason. What's the obvious reason why plugging in a laptop here, causing a fault, doesn't make sense to trip all of campus?
Because then no one else can use the power.
Yeah. One little load problem here, and everybody on campus, 20,000 people, can't do their work or can't learn. What's the other less obvious answer?
It's hard to figure out where the fault is.
Yeah, good luck finding that. I plug that in, and however many millions of loads there are on campus, now I got to go find it. So the least amount of equipment you take out of service helps you go from this to maybe this to troubleshoot and find out where that faulted piece of equipment is. And then you can physically remove it. You can disconnect something. You can, isolate it even further. There's a bunch of different things you can do. So system isolation really helps. And that's the system protection aspect we're talking about there. Let's do some history just briefly. 1880s, Pearl Street DC system, 59 customers. That was the very first quote unquote utility in the world. 59 customers in Manhattan, right? Because Manhattan has been populated for forever. And Edison was in New Jersey. So he's like, let's just do it essentially over the river there. And then a gentleman, Sprague, had a practical DC motor because you could actually have a lot of energy moving from point A to point B. Let's do something with mechanical force because the electricity isn't all that good for doing something that's helpful to us. But if we could have some mechanical force, that would be helpful. So let's do the DC motor. A year later, the transformer came around, but nobody understood how important that was because it was still DC. And then in the mid 1880s, we had the rival AC system. And that was a real challenge at the time to figure out who was going to go forward, AC or DC. If you look back in history, there was some real cruelty if you saw what Edison did to convince people or to try to keep people to switch to AC. Does anybody remember what he tried to do or what he was doing? Scare people away. He would bring wild animals into like Manhattan and he would electrocute them with AC just to show the damage that was done with AC. It was scary, right? You see this elephant being electrocuted. It wasn't the best thing, but it worked. It kept DC in the forefront until Nikola Tesla invented the AC induction motor. Does anybody know why Tesla is called Tesla? Obviously, it's because of him, but why? The first set of motors that drove Tesla vehicles were induction motors. They've now switched to, they're called variable reluctance synchronous motors. But back 20 years ago when they were doing this, they used AC induction motors or asynchronous motors. Some people still call them Tesla motors. And then we had a three-phase transmission line, crazy, operating at 2,300 volts. That was state of the art at the time. Nowadays, going by your house is 13.5 or 12.7 kV. So that's just going by your house. So 2.3 is not very much. Campus, we have 4160 that runs underground. So that's pretty low voltage. 1896, now was the first time we could have a generator at Niagara Falls. And you can still go to Niagara Falls and see the hydroelectric facilities there. 20 miles away, they ran AC lines from Niagara Falls to Buffalo to power the city because you didn't want a lot of coal or all these different things that would produce a lot of emissions in Buffalo. So let's just get clean, energy from Niagara Falls and then just transport it 20 miles away, which remember, this is in 1896. They didn't have, gas cars and all that stuff. It was very difficult to go 20 miles. But with electricity, it was no big deal to go that distance. And in the 1900s, we started to supply or develop all these private utilities because people realized how much better their lives were if they had an electrical connection. And so they started to expand, but it wasn't practical to have 10 different companies providing electrical services to their regions. And so the state started to step in because they were becoming natural monopolies. The first one on the block would get it, and then they could control prices. They could, tell customers, no, you can't connect and all that stuff. So as a result, they actually had to start regulating utilities and all utilities, right? Water, sewer, electricity, gas, used to be telephone, but not anymore, right? Because does anybody here have a landline? I don't. So, yeah. So a lot of these utilities, we don't have, they needed to be monopolized and maintain it. And because they were cost plus, they make a lot of money. Let's have these big interstate holdings that would come in and buy up all the regional ones. And then they would go ahead and they would actually get, 50 companies, 100 companies under one or large umbrella. Remember the concept of general or standard we talked about last class. In 1935, let me move this out of the way. Congress passed a public utility holding company because monopolies were bad things, right? So they forced national regulation and they were breaking up all these monopolies. And so states would get around it. So one company like American Electric Power would be a holding company, and then they would have smaller regional companies to get around some of these monopolies. And so they had to list in each state, and that's the kind of the way they did it. 1935, 1936, the US government realized how wonderful electricity is and how much it would better people's lives. So they encouraged or required these utilities to start expanding their networks into more rural areas. So it was fine to have it in Manhattan, but what if you were out in Westchester? You might not have electricity. And so they wanted to spur more development outside the large cities. And so they actually started requiring people to run electrical wires out there. And then also in the 30s, utilities became vertical monopolies. What's a vertical monopoly? It's the whole package all in one fell swoop. Generation, transmission, distribution, and customer service. That still is somewhat the model today in regulated areas or regulated states like Texas, like Virginia, because those rates tend to be pretty low. They stayed regulated. In other parts where they deregulated, the thought was separating the generation from the bottom three would actually result in lower prices. It hasn't worked out that way, to the best of my knowledge. But deregulation started in the 90s and kind of stopped before 2005, I think, because prices were never really dropping. So it's all in one shop. I'll build the generation, I'll build the transmission, I'll take care of the distribution, and I'm going to bill you for that. So I'll take care of customer service all in one fell swoop. And they would just mark it up. Whatever the costs were, they'd figure it out, and then they'd mark it up 20%, 30%, whatever the PUCs would allow. And again, it was the monopoly. So you had a service territory, right? Makes sense, the terminology. You have a territory that you're servicing, and you're the only game in town. So we didn't have to compete. Bangor didn't have to compete with Orono because they would have two different utility owners. And so because there was no compete there, it was more collegial. And so what they started to do is, hey, I have to have some spinning reserve in my system, and you need to have some spinning reserve in your system. But I don't want to have as much spinning reserve because that costs a lot of money and doesn't really do anything for me. So why don't I interconnect to you, and we'll pool our spinning reserve so that each one of us only has to build a small percentage or maybe 50% of what we normally would do. And then if I have a problem, I can grab power from you and I'll pay you for it, and vice versa. And it was a great, great, great opportunity to save and reduce costs. So as a result, you started to see transmission lines pop up all over, mainly just to do this, to have this spinning reserve. And that's still the reason today that the utility or the grid that we're interconnected to is by far the most reliable system that we can get. You can certainly put up a generator at your house and hope for the best. But if you compare the reliability of having a generator at your house for power, or even two, versus a utility system with hundreds of thousands of generators, it's hard to compete. So that's why we have such reliable power, is because of the interconnection. And we interconnected all the way up to 765 kV. That's the highest, like I said, AC voltage in North America. And prices kept dropping. They kept getting better and better because you didn't have as much spinning reserve. People got more familiarity with the systems. They could operate them more efficiently, more effectively. Costs were coming down. So, hey, this is great. I've got electricity to do all my things, and prices are going down until the 70s hit. Some of you, none of you were alive, I would imagine, in the 70s. I was, but there was a term called stagflation, which is a stagnant economy with inflation. Usually it is the other way around. If you have high inflation, you have an overheated economy. And if you have a stagnant economy, you have depreciation. Your prices tend to go down. But this was the worst. And it was primarily because of OPEC. Everybody heard the term OPEC? It's basically a group of countries, if you will, that have gotten together and have decided we're going to try to control pricing for oil so that we all can get a reasonable amount of profit. And it only works for a small group of countries because those countries, the the fossil fuel is all owned by the government. That would never work in the US because in the US, it's all about profitability. All the companies own all the fossil fuel that they produce. And so if they can make money, they're going to sell. They're going to sell, sell, sell. Whereas if the government wanted to control prices, you could actually say, well, no, we're going to nationalize it. And then they would they would limit the output. It's not the case here. So OPEC really made some huge changes in the system. That's when you saw oil, cars in line to get gas and all that stuff. And all of a sudden now you had to pay much more money for fossil fuels, which means electricity prices had to start going up. And so Congress passed PURPA, which meant that all utilities have to purchase power from independent generators located in their territory. So if you could build a better mousetrap, then the utility was required to go ahead and buy power from them. But again, that wasn't necessarily, didn't really work out that way because they obviously tried to bend the rules a little bit. And so this National Energy Policy Act really changed things because what happened with PURPA wasn't as effective as the National Energy Policy Act, which mandated you will have non-discriminatory access. It is as if the generation that is trying to connect to you is owned by you. It does not matter. And so if you have the criteria met in your system, for your system, then you're required to let them in. There's no additional roadblocks that need to be done. And that was to set up true competition in generation. So again, build a better mousetrap, you will do it. And that has resulted in all this deregulation. So Energy Bill 2005 repealed PUHC, but modified PURPA, again, because the changes weren't exactly happening as we thought. So now we get into 2010s and we start to get into global warming concerns, CO2 production. And in the New England states in New York, there's this thing called RGGI, Regional Greenhouse Gas Initiative, which sort of tries to regulate the CO2 that you can produce. And it's a credit process or system where you're given so much CO2 that you can produce. If you produce more than that, then you got to get those credits from somebody else. If you produce less, then you can sell those credits. Mixed implementation, again, because as a country, we don't have consistent approach to things. So it's very hard when you're doing some things in New England or the Northeast, and in the South they're doing things. It makes it harder for national implementation. But DG is pretty effective. I can just put on a PV array at my house. And if I can put it on and I can be sensible about how to set it up, then I can get generation at my house. And I can stick on a power wall, which I can monitor the PV and I can either charge or discharge the battery based on electricity rates. So if I'm not allowed to use net metering, which basically looks at the net of the amount of energy you take in versus the energy you sell back, and net metering works out really well for a lot of customers who have PV on their homes, because if they have an excess of generation during the day, they bank it, quote unquote, by selling it to the grid or putting it onto the grid. They say it's storing it, but it's not really that way. And then at night, when they need power, they just take it from the grid. Well, the problem is it's not really storing it on the grid. At that point, it's being used. And so you have to buy it back from the grid, hopefully at lower cost, but not necessary. So what was happening is the net metering folks, it can be a little bit unfair for those of us who don't have generation on our homes. And so there's a lot of back and forth about if net metering is fair or not. And so that's why you see a lot of up and down legislation about that. So we're doing the best we can, and competition is supposed to make things better. Again, it really hasn't happened that way because it's hard to compete in this market. There's a lot of regulation. But the idea is you can choose your own electricity supplier. Even in Versant territory or CMP territory, you don't have to do the standard rate. You can opt for a different rate if you want. The standard rate tends to be the most cost effective, but if you wanted to have more green power, you can go ahead and do something like that. Here are some electricity rates, and I don't know, it seems a little bit off, but you can look at Maine, right, where the light purple, and why is it 15 to 20 cents per kilowatt hour? That is mainly the cost for energy. That doesn't include the wires charges. All right. But you don't want to be in the darker colors because the darker colors tend to mean you're paying higher energy rates. And so Alaska and Hawaii kind of makes sense that you'd pay higher rates. But all these other ones, it would seem like they should all be about the same, right? Wherever you are. Well, that just goes to show you like what are the resources, what are the regulations in terms of power. But North Dakota, Washington, Wyoming, less than 10 cents a kilowatt hour, half what we pay for energy here in the Northeast. And then you can understand why that in New York, they were trying to put, $3-4 billion worth of power plants because look at their rates. They're some of the highest in the country. And most of the deregulation, California, the Northeast, why? Kind of obvious, right? Look at the colors. They're pretty expensive in terms of the cost for energy. But down south, hey, I'm paying really low rates. Why would I do that? And you also might start to see too, if you look at the colors, why is it that a lot of industrial manufacturing is happening in the south? Oh, because the electricity rates are so low. You need gobs and gobs of energy to build stuff. So why wouldn't you build a plant in South Carolina, for example, and energy costs are low, you might have to spend a little more money on labor or, qualified labor or engineers to move to those areas, but the energy costs will save you that money in the long run. And then eventually you're gonna have people moving to South Carolina. You don't have to pay as higher rates. So you can see a little bit about, where the populations are, and a lot of it has to do with costs. California and New York, I think, have lost the largest number of people. A lot of people moved to Texas. You can see pretty low prices. I always include this because this is really fascinating at the time. You may or may not remember, but in February 21st in Texas, there were massive blackouts, people losing power for long periods of time. Anybody remember what happened? Big hint is February. It wasn't an ice storm in February. It was a cold snap. Incredibly cold temperatures for Texas. So cold that all these plants, including the wind turbine plants, were not designed to be able to operate in those cold temperatures. When you're operating in cold temperatures, you have to have freeze protection. So water will freeze below 32 degrees. They're usually not used to getting temperatures that low. So all these devices that they're monitoring things, they didn't trust them. They didn't believe them. They thought they were frozen. So they had to shut those power plants down. And even though they had plenty of generation, most of it wasn't allowed to run. And what ended up happening is ERCOT, which manages the grid there, said we have to actually turn customers off. There wasn't a fault. Nothing got damaged that caused it. There wasn't enough generation. And because you have to have that spinning reserve, that spare capacity in the event something does happen, you could have maybe 10, 20% additional generation, but a lot of customers are without power for extended periods of time. This has happened in California a lot, but it's different in California. They're better about it now, but they'll either do brownouts, which means they drop the voltage specifically to a lower level. And the idea is that you'll have less load because the voltages are lower, or they do something called rolling blackouts. And rolling blackouts are really difficult because they turn off neighborhoods. So this neighborhood will have power for 8 hours, and then we'll turn you off and then switch to the next 8 hours and go like that. They didn't do that in Houston because they had never seen it. And it's
and Paul, Texas isn't interconnected.
What's that?
Texas is not interconnected either.
You sure about that?
One of the major problems.
No, Texas is interconnected, but it's interconnected asynchronously. It's interconnected through DC lines, right?
Sure, it doesn't have the same grid stability as like the large regional interconnects of the West or New England ISO, New York ISO.
Well, that could be. I'm not sure why. I mean, they might have been limited because those DC systems can only move so much power. But if you look at Texas is a big state, and they had problems in Houston, which is pretty far south. So you can't move, hundreds of megawatts all the way to Houston without getting large line losses. So, but yeah, they are interconnected. It's just DC. So if you want to read about it, a lot of politics and blaming wind and whatnot as the problem. But it wasn't wind, it was all the fossil fuel. Some of the wind turbines couldn't run because they didn't have a low temperature controls, but a lot of the fossil fuel fired power plants couldn't run because, again, they didn't have enough heat tracing to make sure that their instruments or their piping wind freeze, and so they had to shut down as well. So you can only believe about half the story when you're looking at it on the news. You can do additional digging to get there. That's the other thing too, the Houston gridlock. That's if you remember, there's a senator from Texas who hightailed it out of the state and went to Mexico with his family, I think, and that caused a lot of political blowback. So again, a lot of politicized type stuff. Smart grid, we'll go over that a little bit, but we won't get too much into that because it really uses real-time control to do the smart grid. It really is just digital information and control, more real-time control using computers to be able to make decisions about something. You're going to do grid optimization, so more advanced analysis, more monitoring of parameters, so you don't have to guess, you know what's happening at certain locations. And the last one is getting harder and harder and harder, and that's cybersecurity, right? So obviously nobody here wants to get their stuff hacked, but if you hack into a transmission system or a grid operator, you could shut down, you know, however much power for people, and you could cause real havoc. And so cybersecurity is becoming more and more of an issue. I know a colleague of mine works at Perversant, and he used to be able to dial in and go access information from the Orrington substation. And then they changed the rules for cybersecurity. So you know how he accesses the information at Versant now or Orrington now? He jumps in his car and drives there. All those relays were taken off the network, so you can't actually access them remotely. So you physically have to be on site. So you kind of assure cybersecurity, even though if he brings his laptop there, his laptop has to be checked out and make sure that that has gone through and there's no bugs and all that stuff, because you know you can have cybersecurity problems with that too. So that's becoming a bigger issue. Deployment of DER, distributed energy resources, including, I don't know why the battery storage stuff got cropped off. But you can have customer participation. So the smart grid is enabling you as the owner of the load to make decisions. Hey, I'm really hungry and I'm really have a craving for chocolate chip cookies. I would like to make a fresh batch of chocolate chip cookies, but the price for energy is $800 a megawatt hour. So the utility will send that information to you. If you make your chocolate chip cookies now, it's going to cost you $7. If you wait until like 10 o'clock at night, it'll cost you 50 cents. So it empowers you to make decisions about when I do things. Okay, that's all the smart grid does for the consumer, is it pushes that information over to you. We talked about partial hybrid electric vehicles. If you have a big battery and if you're willing to potentially discharge your battery, you can go ahead and connect and sell kilowatt hours to the grid. Yes, sir.
You think we will have the AI integrated in a sense that they will be able to change the settings into relays, but instead of adjust
No.
the settings?
No, I'd never. The question is, will AI be able to start changing relay settings? And my answer is no, because utilities are afraid of their own shadow, because nobody wants to screw something up. And if AI goes in and makes a setting change, if it hasn't been vetted and tested, then you can have some serious problems with your system. So we don't have trust in AI updating system relay settings in real time. The AI might actually help you come up with settings, and then you got to do the documentation, but real time, it won't adjust settings. Now, it might adjust some control, like flow this or flow that, but I don't believe it'll replace relay settings anytime soon.
Could you see machine learning switching between like different preset setting packages or wildfire settings?
Yeah, so the question is, would you switch between preset settings packages? With AI? No. I think it's such a binary decision, setting one or setting two. Like it really isn't a gray area. That's what the AI does, right? It allows you to kind of make interpretations or make assessments about things, where generally speaking, if you're making a decision to go from A to B or 1 to 2 in the utility world, that's I have to have a lot of things. I have to make sure that these things are happening before I switch over to 2. I don't want to make a mistake. So I don't think AI will do that. I think it's just, there's not enough learning that can be done. There's not a lot of trust. Getting data is even very difficult. So I don't see that happening anytime in the near future. Maybe many years from now, But yeah, I don't see that. Although it's too bad because they could optimize things. There's too much risk for many people to do that. Do you have a question?
They are doing a research here. I know a guy doing downstairs.
Yep.
The lab, they're doing research about kind of having the AI into the grid too.
Sure.
Is doing it.
Yeah, that's research. Will it get deployed out on the grid? Maybe on a test bed, like a military facility where you're not going to have the same problem. But to do widespread implementation of something, yeah, I don't see that happening anytime soon. And a lot of it has to do with how NERC sets things up. It mandates you have to have all these knowns before you can even, you know, pull the plug on something. So there's just too much risk. And it works. It's cost, you know, it's not cost prohibitive right now. Maybe if something major happens, like, you know, we need so much power and we can't build it for whatever reason. Okay, then, you know, it becomes more extreme and now we have to make some decisions about accepting lower reliability. But right now, reliability is king and the system works as it's intended now. It's just not worth the risk to add all this other stuff.
And then if AI mess up, who are we blaming for?
That's exactly it. Who's to blame? If I'm losing power, I'm blaming the utility. I don't care if it's the AI model that made the decision. I blame you because you're the utility. You should have not trusted AI. You should have had backups. It's just the blame game. And then making sure everybody communicates with each other. Some sort of interoperability, because we don't want to use custom, you know, packages for settings and development and all that stuff. It just makes it too hard. We got to be able to use the same set of equipment and settings, development stuff so that it all works together. So you can see between less smart and more smart, you get your outlet on the top left. Let's go in a counterclockwise direction. That's how you used to run the grid on the bottom there. You had a couple lights and you had, you know, a screen and you had a bunch of meters, and that's what the operator did it that way. Then the lower right is ISO New England's. That's their control room in Hadley, Massachusetts. I actually did have an opportunity to get a tour in there a long time ago. Again, it's just getting tighter and tighter to get into these places. But you can see this one person working. He's got 7 monitors plus that little monitor that's below. So maybe 8 monitors that they're staffed 24/7 to monitor the system and make decisions about what we need to do. Then they have the big board, which anybody can look up and monitor power flows, bus voltages, and that type of stuff. The top right, I just included that here. If you remember from like maybe 10 years ago, that's a scarecrow dancing a lot around a transmission system. Anybody have an idea why there's a scarecrow dancing around a transmission system? The Wizard of Oz. Who was the scarecrow? What was he missing? The brain. So if the grid is dumb, doesn't have any brain. So the scarecrow is bouncing around happy that the grid is going to get a brain because that was just synonymous there. I thought that was pretty clever marketing or advertising for pulling that together. And if you watch the video, he's singing along to the Wizard of Oz, If I Only Had a Brain. So that dancing around was just, whoever came up with that marketing thing was really smart. And you can still find it on YouTube. So if you've got nothing better to do and you want to see that, that's pretty cool. Some requirements for renewables. Again, down south, not a big demand. Okay. And, you know, what are the reasons for that? Maybe they don't feel they need it. Maybe it's too cost effective. Cost prohibitive to do that. Kind of hard to put a lot of hydroelectric in Florida when, you know, there's not much of an elevation change, right? Hydro doesn't work so well down there. Maine, piece of cake, right? Because we got tons and tons of hydro. As you saw, there's about 80% of renewables in Maine. So easy peasy. I always go back to Texas. Texas even has RPS requirements. But it's great wind resources there. So it's an easy, low-hanging fruit. So what I say about this is just be careful because a lot of these states are doing it because it's not hard. It's not a hard goal to get. And then the other ones that it's more difficult to get, they don't even bother. I get to work on this project. So there's an industrial park in Rumford, Maine, and this is the first commercial scale battery project in Rumford, Maine. It's 4.99 megawatts, because once you go to 5 megawatts, there's different treatment of the systems. So anything less than 5 is a lot more cost effective than 5 and over. So that's why it's a really odd number of 4.99. But it's just a battery, and how these batteries work, all they are shipping containers. So if you were to go to like a shipping port, and if they move shipping containers in and out, those are the same structures. They house cabinets with racks full of batteries. They have some controls on them. And then on the top, they have cooling systems because they generate heat, right? They're not the most efficient, and so they generate heat. And so this is a small one, and it connects or interconnects to the distribution system because it's only 5 megawatts. You don't need to interconnect to the transmission system. Yes, sir.
Are there more battery banks like that now, or that's nothing?
There are more, yes. Yep. There are definitely more. It hasn't exploded like I guess people thought. Part of that is because remember how we said in Maine, you're not allowed to own generation? Is CMP allowed to own the battery storage? Is it a generator? Maybe. Is it a load? Depends, right? So I think the PUCs have made exceptions for battery storage because you're really not generating electricity, you're storing it. But it does get into a whole different set of quandaries, because if I turn this battery system on when power prices are really high and I start cranking out megawatt hours, I don't have to pay as much, and I can actually make a little bit of money when I'm exporting that power. So all the generators around that can only get on when the demand is there. They don't have the storage capacity or capability. They're upset about how the pricing mechanism works. So there is a lot of problems with that. I know in Lincoln, the old paper mill, they were talking about building one of the world's largest battery storage facilities, but I think that that's probably not going to get built. I think. Just a couple of years ago, I worked on a project in Bradley, Maine, which is just 20 miles from here. They were going to build a 110 megawatt PV farm, but that project died because, again, things change in politics, and so they're not building it now. But that would have been the largest in New England if it would have gone forward. So just 3 battery containers, not too big, small scale, very modular. You can just add on modules as you need more or less power. As long as the transformer that you interconnect to and the breakers are big enough, you can just add modules on all day long. Very, very effective way to do it. So very, very cost effective. What do you notice about this picture? You see load and generation. Is there any kind of key things? The purple is where the generation are. The load is pretty much where the lights are. You notice anything unique about it? Yes, sir.
The east side is much more populated than the west.
East side. What else?
They're all co-located.
They're all what?
Co-located.
Co-located, so the generation tends to be fairly close to the load. Anything else?
There's no production of wind.
Relatively small, right? When you look at all of the US. I notice the load, all the lights tend to be pretty close to the coast, don't they? Yes, you have some in the middle, but if you look at the middle, which is not just here, but also here, right? Look at the amount of load that's on the coast or within 50 miles of the coast. So even in the United States, more people live near the coast, within 50 miles of the coast, than they do away from the coast. So why is that a challenge? Because over here is wonderful, wonderful, wonderful wind resources. If you could take North Dakota and you could capture all the wind that's in North Dakota, you could power all of the United States. But nobody lives in North Dakota. And it doesn't make sense to put a lot of generation there when you're going to move that power 2,000-3,000 miles to get to where the load is. So you can move power. We talked about it's a great conductor. I mean, a great conveyor of energy, but it comes with limits. So in Maine, we have fairly long transmission lines, 80, 90 miles in length, but that's typically not what you see. You try to get your line lengths to be smaller. So your generation tends to be fairly close to your load, 30, 40 miles away. So it's not practical to put all your generation in the middle of nowhere and run, thousands of miles of electrical conductors or transmission lines to get from point A to point B. That's why Maine Independence Station is down here on the river. It's like 5 miles from campus, not because campus is so much load, but because you have Bangor, and Bangor has a decent amount of load, so you have some load there, but then you're still moving power down to the rest of the state. So you've got to put generation close to the coast, which is wonderful for offshore wind. How much closer can you be to the coast if you're actually in the water on the coast? So why does offshore wind have such potential? Because it's close to where the people live. You don't need to run long transmission lines. So you can reduce the utility interconnection cost dramatically, but putting wind turbines up that are 400 or 500 feet tall, 5 miles off the ocean, 5 miles off the coast is not a cheap endeavor. Maintaining it is not cheap. So there's some things that need to be worked out. In Europe, they've been doing it for many years. But I think if you go where those are effective, they tend to be shallow, not as deep as some of the places you see up in New England, but great wind resources. California, along the coast of California, has wonderful wind resources. Off the coast of Maine has great wind resources too. Once you start getting down to Florida, it's not as good, but that's some of the things to think about. I think this is my last slide, but what we're going to focus on for time scale is pretty much here. And we're going to look a little bit at here. Fault analysis and power flow. So one is a steady state analysis, and one will be what we would consider a transient. So you can look at the time scales we're talking about. We're not going to look at 10 to the -6 because that's lightning. That's a different way of treating it. Sorry about that. And we're not going to worry about unit commitment because that's when you decide when plants will turn on and try to minimize the costs of electricity. So we're going to just focus on that. But this is why this field is so exciting. I mean, look at all the different things you can study just in the power. Are there 10 different things in different time zones or different time frame? So really can do a tremendous amount with this. And once you start getting over here, lightning, there's really nothing you can do other than survive, basically. So there's not much you can do there. But over here, you can use some smart devices and you can really make things go. And the faster we can respond to things, typically the better the outcomes will be. And that's limiting even fault currents. So there are things called current limiting fuses that actually, if a fault occurs and it wants to pull 400,000 amps, the current limiting fuse will act to take that potential 400,000 amps and knock it down to like 50,000 amps. Way less damage happens. Anybody know how that happens? How you knock down with a current limiting fuse? Go ahead.
Really high enough to run up current going through it gets hot enough that the chemical property does changes and it becomes less conductive, so it effectively becomes a restricted.
So that's part of it, but usually the current limiting fuses, and this is for our chemists in the class, what happens, so these bimetallic elements or the mixed metal elements, they're getting current through it, and they're supposed to be low current, a low heat, low impedance so that you don't have a lot of heat. When they get hot, what if I stick sand around it? What happens when sand gets really hot? Turns to glass, right? And glass is a really bad conductor. So as you're forming glass inside the fuse, it's making it so that it's harder and harder and harder for the material to conduct, because the no electrons are flowing glass. The very first insulators were essentially glass. And so that's how you can get current limiting fuses. Those are simple, dumb fuses, but they still work very, very well. And they do a really good job. All right, questions on anything? I promise I'll get into more technical stuff in the next class, but it's sometimes nice because I have such a wide variance of folks that are in this class. So it's nice to get background information, but also hopefully get you excited about what's going on, what is happening in the grid. And looking at why you pay what you pay for electricity. So instead of riding those scooters, right? I see the scooters everybody's riding around campus, or the skateboards that have batteries in them. Actually use your legs. Save us some energy. and you'll be healthier along the way, right? I was riding my bike this past summer and I was riding around a lake. This guy's on a mountain bike and he blows by me like I was barely moving. I'm like, I'm not gonna let him blow by me, so I catch up to him. He's on this really fancy bike. I'm like, how are you doing this? Oh, this is an e-bike. He was barely pedaling and the e-bike was doing like 20 miles an hour. And I'm like, I'm not trying to catch up with you. I got no chance. So the world has changed. I guess that's for the good. So, all right. Any questions, TV land? Did the video link come across okay? I checked it out and it seemed to be fine, but it's always good to check. The quality usually is HD quality is what it says. It takes time to get HD quality. That's just what YouTube takes to process it. But I think it's 1040p when it's all said and done. So the quality should be pretty good. But everything worked okay? Good.
Yeah,
Okay.
everything's worked well for me.
Good. Thanks, Doc. All right, y'all. Have a great weekend. If you're having questions about lab, empower yourselves. Look at the syllabus. The lab details for next week are all contained in the syllabus, okay? All right, take care, everyone.